So this is the derivation for the temperature change in a reversible adiabatic expansion. So just to break down the conditions a little bit more, reversible means that the external pressure is equal to the pressure of the system. Adiabatic means that the net heat transferred is equal to 0 joules, and the internal energy is therefore equal to work. So expansion in a reversible adiabatic setting entails that work is equal to negative p dV. So there are three steps in this derivation. One is to write an expression relating temperature and volume. The second is to integrate the expression, and the third is to simplify. So for the first step, we want to write an expression relating temperature and volume. So if we look back to our conditions, we'll see that some of the equations that may be important here are the relation of work to negative p dV. So I'll just write that down. dW is equal to negative p dV, and this is also obviously applicable to adiabatic work, so I'm just going to make that clear with a subscript. Adiabatic work is equal to negative p dV. So according to the first law, du is equal to dq plus dW. So energy as heat and energy as work. In an adiabatic setting, dq is equal to 0 and du is equal to dW AD. We also know that du is equal to the heat capacity at constant volume multiplied by dT. We basically just kind of get this from the expression for the change of internal energy with I'll write that down, with variables t and v. So du is equal to the partial derivative of du over dv, constant t, dv, plus change in du over change in dt at constant volume dt. So in an isovolumetric setting, this is 0, this is 0, and du is equal to partial u over partial t at constant volume dt. So this term is CV, this is dt, and that is where you get CV dt from. But this isn't to say that we're deriving this under a constant volume setting. That's just where this ideal gas equation comes from. So here we have our necessary sort of equations. We have dW adiabatic is equal to negative p dV. du is equal to the work done in an adiabatic context, and du is equal to CV dt. So we also know that dWAD is equal to CV dt just by substituting right there. So because these two are equal, we can now equate these two expressions with each other. So negative p dV is equal to CV dt. So because we also know that this is a perfect gas, we can substitute the expression PV equals nRT, where P is equal to nRT over V, and we can substitute that into our equation. So negative nRT over V dV is equal to CV dt. So this is great, except it might be helpful to move the t variable over to the dt side. So there we have negative nR dV over V is equal to CV dt over t. So this is our expression, and that is step 1. Next step is to integrate the expression to find the overall change. So we can assume that the heat capacity at constant volume is constant over the change in temperature here. And then we can also know that nR is constant. So when we integrate this expression, we can take it out of the integral. Negative nR integrated from v initial to v final dv over v is equal to Cv integrated from the initial temperature to the final temperature dt over t. So that leads us to negative nR natural log v final over v initial is equal to Cv natural log final temperature over initial temperature. So here we kind of just want to remove this negative sign. It's a little bit inconvenient for later purposes. So in order to do that, we just flip the term inside the natural log, and then we can get rid of the negative sign. So nR natural log v initial over v final is equal to the heat capacity at constant volume natural log of final over initial temperature. Okay, now we essentially want to get rid of these constants or simplify the constants. So I'm going to move this nR over to the Cv side, and now we are left with natural log of initial volume over final volume is equal to Cv over nR natural log final temperature over initial temperature. So this term, we can introduce a constant, C constant, which is equal to Cv over nR, or the molar heat capacity at constant volume over R. So that's what C means. So we can rewrite with that C in place. So using the relation a ln x equals ln xa, we can move this C as an exponent of the term inside the natural log, and now we have this. So if we raise it to the power of e, raise this term, or raise e to the power of this term, we can cross that out, and we find that vi over vf is equal to tf over ti to the power of c. So normally this equation is written out like this. Final temperature over initial temperature is equal to initial volume over final volume multiplied by 1 over c. And then we rearrange to find the final temperature, which is equal to the initial temperature times the initial volume over the final volume to the power of 1 equal over c, where c is equal to the molar heat capacity at constant volume over R. Also, you can write it like TFCVF is equal to TICVI, where the C is with the temperature term. And that's the derivation for temperature change of a reversible adiabatic expansion.